Let's take a look at a quadratics application word problem dealing with the volume of an aquarium together. An aquarium is designing a new exhibit to showcase tropical fish, and the exhibit is going to include a tank that is going to be in the shape of a rectangular prism. So if we know the aquarium is going to be in the shape of a rectangular prism, it's going to look something like this. Now, if we know we're talking about a rectangular prism, then that's going to have three different dimensions where we're going to have a length as well as a width and a height. Now, in terms of the length, we're told that it is going to be twice whatever the width is going to be. So we can say that L is going to be equal to 2W. And for the width, we don't know what that's going to be, so we can just use that variable of W to represent the width for now. And then finally for the height, this is going to be that third dimension. We're told that the height of this tank is going to be 3 feet tall, so I'm going to say the height is going to be 3. So keep in mind that it's really important to know that the length is twice the width here, which is why we can go ahead and express the length as 2 times whatever the width is going to be. Alright, so now that we've set up this problem and we know what is going on, let's go ahead and see what other information that we're given. So we're also told that the volume of this tank is 420 cubic feet, so I'm going to go ahead and say that V is going to be equal to 420. What we're being asked in this problem to do is to figure out the width of this tank measured to the nearest tenth of a foot. Alright, so now that we've labeled all the pieces to our problem, let's go ahead and set up an equation here. So try to recall that when we're dealing with volume, volume is going to be capital V. That's going to be equal to the area of a base multiplied by the height. And this applies to all of the different types of prisms that you could work with. Now, in particular, for a rectangular prism, the base is a rectangle. So we can replace capital B, or the area of the base, with length times width. And then we're going to go ahead and have that height here as well. Now, what was the volume? Well, we knew the volume earlier was going to be 420. So if you go ahead and take that information of 420 and substitute that in for this variable, the volume is 420, and that's going to be equal to, and then we have the length here. Now, instead of having the variable of L, we can also write L as 2W. So let's go ahead and write that in. So the length here is going to be the same thing as twice the width, because it's always going to be double of whatever the width is going to be. As for this W, well, we don't know what W is. The width is just going to be W. So let's go ahead and just substitute in W for W, or just copy that. And then finally for the height here, remember we were told that the height of this is going to be 3. So let's go ahead and just substitute in the value of 3 for the height. Alright, so we have an equation here, and we have just one variable, so this is going to be a little bit more straightforward to solve. The left side we're just going to leave alone for just a moment. On the right side, it looks like we just have a bunch of multiplication. We have 2 multiplied by W multiplied by another W and a 3. And so by the commutative property of multiplication, we can just go ahead and rearrange this. Let's go ahead and put these values in front here. So it's going to be 2 multiplied by 3. And then we have these 2 W's that are going to be multiplied together as well. So it's going to be multiplied by W and W. So if we go ahead and then clean this up a little bit, then we can go ahead and say that 2 times 3 is going to be 6, and then W times W is going to be W squared. So here we have a quadratic equation. Now if we're going to go ahead and solve for W, the first thing we're going to want to do is get its coefficient to be 1. So we can do that by dividing both sides by 6 using the division property of equality. Now 420 divided by 6, we know 42 divided by 6 is 7. So 420 divided by 6 is going to be 70. So we have 70 is equal to, and on the right side, 6 divided by 6 is 1. So we just have 1 W squared, or just W squared. All right. At this point, we know that if you square W, you get 70. So what's the inverse operation of squaring? Well, it's going to be taking the square root. So let's go ahead and take the square root of both sides of this equation. If we do that, the square root of 70, there's going to be 2 versions of this. So I'm just going to write plus or minus the square root of 70 for now. And on the right side, the square root of W squared is just going to be W. Now I'm just going to go ahead and turn this around a little bit just because I like writing my variable on the left side. So we can say that W here is going to be equal to this plus or minus square root of 70. And if you go ahead and plug that into a calculator, we would say that the width of this is going to be about positive 8.37 if you round it to the nearest hundredths place here. But you could also say that W is about negative 8.37. So algebraically, you would get this positive or negative version here. Now I just wrote 2 decimal places here, and the problem does say that we want to round this to nearest tenths place, but for the sake of just being a little bit more accurate, I wrote to the hundredths place. And so while we did algebraically come up with these two solutions of positive 8.37 roughly and negative 8.37, if you go and plug those into our equation here, they both will work algebraically. However, this is a contextual problem or an application where we're talking about an aquarium and the lengths of this rectangular prism. So keep in mind that only one of these solutions actually makes sense here. And so what we're going to conclude here is that the width of this aquarium is about 8.4 feet long. Let's see if this makes sense. If we go back to our original problem here, and we go ahead and actually substitute in some values, let's see if this makes sense. So we have about 8.4 for W. So if we go ahead and take this information and see if this makes sense with our expressions here. So we're saying that W is about 8.4. If we plug in about 8.4 in here for W, and then we know the length is going to be double whatever that's going to be, then 2 times W would be roughly 2 times 8.4, so that'd be about 16.8, right? And so if you go ahead and take a calculator and you multiply the length and the width and the height together, that should equal the volume, right? So in this case, the length is going to be 16.8. So if I take 16.8 on a calculator, multiply that by 8.4, and again, these are rounded, so this should be approximate, right? So times 8.4, that's going to be about 141.12. And if we multiply that by 3, I'm getting this is about 423.36. And so I would say that's pretty close to this 420 here. And there's a little bit of wiggle room here just because we rounded to nearest tenths place. So there's going to be a little bit of error. All right, so that's how you take the information that we were given about this particular aquarium, set up a quadratic equation, and solve it to get our two solutions for this particular problem. And one of them didn't really quite make sense because you can't have a negative dimension of an aquarium, so we just used the positive dimension. We rounded to the nearest tenths place, so we know it wasn't perfect because it was an irrational number. And so we got an answer, and if we plug it in, we do get approximately the correct volume, but it's going to be a little off because we did some rounding. If you found the video helpful, please consider giving it a thumbs up and sharing it with a classmate or friend who might also find it helpful. And as always, keep up the great work that you're already doing.